Okay, let's dive straight into this explainer and look at a modern phenomenon we've all probably experienced by now. You know the drill. You sit down at your computer, you type out some completely wild sentence, maybe something like, an astronaut riding a horse on the moon, photorealistic. And you wait, 10 seconds? Then suddenly you've got this fully formed, highly detailed image looking right back at you. It's an image that has literally never existed before, of an event that never happened, rendered in a style nobody actually drew by hand. It's the absolute illusion of typing a prompt and getting reality delivered right to your screen in just seconds. So naturally, the very first question that pops into our heads when we see this happen is, well, is it magic? I mean, it certainly feels like magic to just conjure a flawless image out of thin air, completely from scratch. But as we're going to see as we unpack this today, there is absolutely no magic involved. Actually, it's an incredibly strange, highly clever trick that's essentially being played in reverse.
And this really hits the nail on the head regarding the core reality of the technology. The AI didn't actually learn how to draw. It didn't take art classes, and it definitely doesn't understand brushstrokes or lighting or composition the way a human artist does. Instead, it learned how to clean up a mathematical mess. It's fundamentally a janitor of pixels. And to understand how a mess turns into a beautiful picture, we really have to look at how these systems are built from the ground up.
Which brings us to part 1, training with static, or in other words, destroying pictures.
To understand how these tools generate a brand new image today, we actually have to pull back the curtain on a very counterintuitive starting point. The training process literally begins by destroying pictures in order to build a robust data set for the AI to study. Researchers take millions upon millions of crisp, clear, real photos, and then they gradually begin adding random visual static to them.
They do this really systematically, step by step. They take that clear photo, let's say it's a picture of a dog, and corrupt it frame by frame with more and more of this visual static. They just keep going until the original image is completely buried. By the end of this step, the original photo is totally unrecognizable to the human eye. All you're left with is a square of complete random digital noise.
Next, a neural network is introduced to the process, and it's trained to do one very specific, highly focused job. It is asked to look at that completely noisy image and predict exactly what noise was just added to it. It's essentially trying to figure out the mathematical formula of the static that's currently hiding the picture.
And right here is where the incredible trick begins to take shape. Because the network successfully predicted the static, it can mathematically subtract that predicted noise back out of the image. By doing this in reverse, step by step, the network slowly peels away the static, revealing the clear, original photo of the dog that was hiding underneath the whole time. It quite literally learns to reverse the destruction.
So the absolutely crucial point here is that researchers forced the network to do this millions of times on millions of different images. Through sheer brute force repetition, which by the way requires massive data centers and just immense compute power, the network becomes a master, an absolute expert at one very specific skill: denoising. It masters the art of turning noisy static back into something that looks like a real photo again. This entire foundational process of removing noise is what we call a diffusion model.
All right, let's move to the performance phase in Section 2, hallucinating photos, starting completely from scratch.
Now we face a really fascinating question. We know the model can take static and reveal a hidden photo, right? But what happens if there was no original picture hiding underneath the static to begin with? What if you just hand the model pure random noise that was never a real image in the first place?
Well, the fascinating answer is that the model just does its job anyway. Step by step, it confidently predicts what noise to remove and it subtracts it out. But because there was no original picture, the model is essentially hallucinating a photo into existence. It's guided entirely by the statistical patterns it learned from all those millions of real training images. And because it starts with a totally unique pattern of static every single time, you never get the exact same image twice. As a result, random noise pattern A might give you a completely unique sci-fi landscape, while random noise pattern B gives you a totally different neon cityscape. The model creates something unique every time because the starting static is always unique.
Which logically leads us to Section 3, your prompt as a compass for guiding the AI.
Now, if the system is just removing random noise from a blank canvas, how does it know what you want it to make? I mean, on its own, random denoising would just produce a random generic-looking image, a landscape, a face, something totally disconnected from what you actually typed. To bridge this gap, a second language model is brought into the fold. This language model converts your words into high-dimensional math vectors, effectively embedding the meaning of your text to act as a steering wheel or a compass for the image generator.
Let's break down exactly how that compass works. At every single step of the denoising process, the model pauses and checks that mathematical compass. It uses it to nudge its noise removal choices directly toward your specific prompt. For example, if you typed a cat wearing sunglasses, it removes noise a little more toward cat features and a little more toward sunglass shapes. It repeats this nudging process dozens of times over. Slowly but surely, the random static actually resolves into an image that reflects your specific requested words, rather than just generating any old plausible-looking picture. Of course, anyone who uses these tools knows they aren't always perfect, which brings us to Section 4, Why Details Go Wrong and the Limits of AI. This whole process brilliantly illustrates how the image is built, sure, but it also completely explains why AI sometimes messes up complex details like hands or text or reflections. We really have to compare how we think versus how the AI thinks. We operate on human rules, absolute facts, like the unbreakable rule that hands have 5 fingers. But the model? It never actually learned absolute human rules. It only learned through AI learning, which relies completely on statistical patterns of what shapes tend to appear near other shapes, all based on its massive set of training data.
And that right there brings us to the infamous problem of AI hands. Because things like hands are incredibly complex, dynamic, and bend in so many weird ways, they're captured from wildly different angles across the training data. Because of this massive variation, the statistical pattern is genuinely harder for the AI to nail down consistently. Think about it. It is so much easier for it to figure out the statistical pattern of a simple uniform blue sky or a flat brick wall than it is to piece together the chaotic geometry of human hands based purely on static removal.
All right, let's wrap all of this up in Section 5, the magic trick revealed. Now, newer models are getting dramatically better at fixing those small details through better data and added refinement steps, for sure. But the underlying process, it remains exactly the same. What you should really take away from this explainer is a fundamental shift in how you view these tools. The AI is not painting a picture like a digital artist, and it is definitely not searching a database to collage together a bunch of matching photos. It is literally starting from pure random visual static and carefully, mathematically guessing its way back to a picture that never existed. It unnoises the canvas one tiny step at a time, guided entirely by the compass of your words. It's a remarkably strange, roundabout way to make a picture, but it leaves us with a fascinating question to explore. If this is how we hallucinate a single still image from pure static, what happens when AI applies this exact same idea across time, frame by frame, to generate completely synthetic video? How in the world does the AI keep the static organized as time moves forward? Now that is a truly mind-bending puzzle, and I'll leave you to ponder that one until next time.